Hello everybody and welcome to video 2 of our exploration into complex numbers and how they connect to polar numbers. So what we did in the first video was what you see underlined in blue here, where we took our numbers, our complex numbers, we added, subtracted, multiply, and divide, and then we plotted them in the complex plane. For the second part, for our second video, we're going to work on first converting these numbers between the two forms, which I kind of teased a little bit in the last video. And then afterwards, we are going to find products of quotients in polar form as opposed to rectangular form. So this idea of multiplying by the conjugate and FOILing over and over again, definitely something that's important, but hopefully we're going to see in a polar form, it ends up being so much more beautiful, which is where we're heading. So let's look at our conversions. To do our conversions, we're going to have our 4 equations that we've been working with all chapter, really all of trigonometry, that we know our radius is going to be, officially it's plus or minus the square root. We are going to work with kind of like our principle, which is a positive radius, and then with our positive radius, this angle is going to be based off of what quadrant we're in. Which, if you think about what we did in 9.1, we did something very, very similar. We are just now doing this on the polar level. And then talked about x is r cosine theta, y is r sine theta. This is really exactly what we've been doing all semester. So this one's actually easy to show, that if we take r cosine theta, if we distribute that radius through, we will get I times r sine theta. And so that easily shows us that our cosine theta is our x coordinate, and then our sine theta is our y coordinate. So that's where we get our x plus iy. Excuse me. So this is where we say, what is it that the theta and the radius, or where do those come into play? If we look back up here at our graph, the radius, once again, is that distance from the pole to that complex number z. And then our theta ends up being the angle that comes off of the polar axis, or in this case, it's the real axis. So let's go back to how do we convert these between our two polar form. Before I actually do this conversion, I want to get an idea of, could I anticipate what this radius is going to be? Can I anticipate what this angle is going to be? So if you notice, this 3a actually models Z1 that I have here. So I'm going to zoom in on Z1 to say, is there a way that I could figure out what this radius is? And that's where I think, wait a second, what is that radius? That radius, if I use Pythagorean theorem right here, that radius allows me to say 1 squared plus 1 squared is 2, square root of 2, which ends up being a radius. So I kind of jumped through some math there, I apologize, but this ends up being the square root of 2 as a length. Now, what angle forms that? We should know that this is a 45-degree angle. We can actually see that 45-degree angle on this graph. So we should end up with a radius of the square root of 2 and the angle of 45 degrees. Now, let's actually go ahead and confirm that I know that x is 1, so x is 1, y is 1. I know we don't see it, but that's 1 there. So our radius is going to be the square root of 1 squared plus 1 squared. Everybody, this is just Pythagorean theorem like I showed you on that graph. And then theta is going to be, I'll go ahead and say the tangent of theta is y over x, so 1 over 1. So this says tangent of theta ends up being 1. Now, what I like to focus on is this is in quadrant 1. And kind of like I showed with our chapter 9 video, or 9.1 video, that we need to make sure we know what quadrant we're in so we can actually work with that angle properly. Because tangent's 1 in both quadrants 1 and 3, but in order to find our angle has to be the quadrant 1 version of it. So what is the inverse tangent of 1 in quadrant 1? That would be pi over 4. So we can write 1 plus I in the form of r, which is square root of 2, and then cosine of pi over 4 plus I sine of pi over 4. So really, I'm having a few technical difficulties here going back to this. All right, so really, this 1 plus I in its polar form looks like that. And I know some of you are going, that really does not look much more efficient. In fact, that looks scarier. That's fair. You'll see where we're going with it though. So our second one, I'm going to go ahead and do in the teal color, because if you notice, I've actually matched up all of these with these numbers. So for part B, our radius is going to be, well, first let's identify x is -4 and y is -4. So our radius is going to be the square root of -4 squared plus -4 squared. So that'd be the square root of 16 plus 16. So square root of 32, which ends up being 2 times, oops, try that one more time. So square root of 32, which is 4 times the square root of 2. Now our theta ends up being, let me write it as tangent of theta, is -4 over -4. But this is in quadrant 3. And the reason why that's important is because theta ends up equaling the inverse tangent of 1. But this time we're in quadrant 3. So our theta is going to be 5 pi over 4. So -4 minus 4i, we can actually write as our radius, which is 4 square root of 2, and then cosine of 5 pi over 4 plus I sine of 5 pi over 4. There's our polar form. And then for part 3, once again, a few technical difficulties here. I think there's a lag between and my mirroring software. So -8i, the -8i hopefully is something that I could expect you guys to do without a whole lot of conversion. If I think about where -8i is down here. Once again, all of these are matched up properly. So -8i, what is the radius, meaning what is the actual length to get down there? Well, hopefully that's obviously 8. And now what is the angle it takes to get there? That would be 3 pi over 2. So let's go ahead and actually work that out. So our radius ends up being square root of 0 squared plus -8 squared. That again gives us 8. And our theta is going to, how about tangent of theta, is y over x. So that y value is -8, x is 0. And everybody, this is why I showed it on the graph, that I now have tangent of theta is undefined because we can't divide by 0. Now, where it's undefined, that's kind of why we need to be able to say, oh, that angle's down here. Tangent is undefined at either pi over 2 on the quadrantal or 3 pi over 2. We have to say 3 pi over 2. So r is going to equal, no, not r, excuse me, -8i in its polar form is going to equal 8 cosine of 3 pi over 2. I'm not sure why I put some parentheses there, plus I sine 3 pi over 2. All right. Now let's do our conversions backwards. If we have this, we're going to our rectangular form. So we have our polar form, we're going to go to our rectangular form. Honestly, it's just easier to distribute first, kind of like I showed you on that mini proof up above. So cosine of 7 pi over 4 is cosine, so 7 pi over 4 is in quadrant 3. So that'd be 8 times, cosine's positive, so square root of 2 over 2. However, sine is negative, so 8i times negative square root of 2 over 2, which gives us 4 square root of 2 minus 4i square root of 2, which, if you notice, is what we had in part B over here. So that was our Z1 from part B. Our Z2, then, just kind of like as a quick, our Z2 should end up being just positive 2i. Now, how do I know if it's going to be positive 2i? Well, let's go ahead and prove it. So 2 cosine pi over 2 plus 2i sine pi over 2. we know that the cosine of pi over 2 is 0, so that's 2 times 0, and the sine of pi over 2 is 1 plus 2i, which, once again, that is 2i. So this should end up being the z3 that we got above. So cosine of 5 pi over 4 is negative square root of 2 over 2. And then sine of 5 pi over 4 is also negative square root of 2 over 2. Let's go ahead and put that in parentheses just to clean that up. So negative 2 square root of 2 minus 2i square root of 2, which, just as a quick confirmation, yes, that's what we're supposed to have. Now, why did I work with all the numbers that I had up here from before? It's because, and everybody, this is the beauty of our polar numbers. So if you notice, and I'm going to go ahead and zoom in right here, if I take z1, so if I take my z1, I know this is pi over 4. Let me go ahead and work with it in degrees just because it tends to be a little bit cleaner to see it. So if I take that 45 degrees, and then I take where z2 is, we go ahead and do this down here. Oops. So if I take my z2, which is right here, that would be 225 degrees. So what happens if I take my 45 degrees and from that 45 degrees, I add 225. Together, that equals 270. Now, it's not a coincidence that that 270 is the angle of Z3. So this is the beauty, this is what I love about this. You can hear the excitement in my voice, that if we are multiplying two complex numbers, like I'm showing that right here, if I'm multiplying, what that does is it really just adds the angles in my polar form. So by multiplying the complex numbers on a polar level, it tells us exactly what angle we're going to be working with. But wait, there's more. So if I look and say my radius is the square root of 2, and I take that radius times the radius of the other one is 4 square root of 2. If I multiply those two numbers together, we magically get this 8, which is the radius of the third point. So, moral of the story, what's going on here? On a polar level, what we could do is we can actually just add the angles to figure out where we are on the polar plane. And if we want to know how far out or how far away, what the radius of that polar number is, we multiply the radii. And that can be summarized by what I have right here. So if I take z1, if I take my first complex number and my second complex number, the way that I find it is I will be find the product. I will be adding the angles and I will be multiplying the radii together. So let's go ahead and actually show that for problem number 5 here. So if I want to take z1 times z2, now notice how I already have this in its polar form. What I will do is I will multiply the radii, so 14 times 2, again multiplying the radii, r1 times r2, and then cosine, I will be adding my two angles, so 2 pi over 5 plus pi over 10, plus I sine of 2 pi over 5 plus pi over 10. Now 2 pi over 5 plus pi over 10, that would be 4 pi over 10 plus pi over 10, which is 5 pi over 10. So let me show that. 2 pi over 5 plus pi over 10 is 4 pi over 5, 4 pi over 10 plus pi over 10, which is 5 pi over 10, or a very happy pi over 2. Ooh. So if I multiply these two numbers together, I will get 28 times the cosine of pi over 2 plus I sine of pi over 2. Now, what's kind of standard is, do I know this angle or not? If I know this angle, let's go ahead and put it back into a rectangular form. So maybe I should add this to the directions. Put in rectangular if nice. Put in rectangular if the angle is known. And I'm having, once again, a little technical difficulties. So if we have a known angle. So that gives me 28 times 0 plus 1i, or just simply 28i. Now, when I have the second one, I don't know if you remember from chapter 7 that if we take pi over 2, the cosine of that is square root of 6 plus square root of 2 all over 4. So if I really wanted to multiply these in rectangular form, this ends up being an extremely nasty product. So do we want to do that? No, this is exactly why we use our polar form. Let's go ahead, take Z2 and convert it into a polar form. So to do that, our radius of Z2 is going to be the square root of square root of 2 squared plus square root of 2 squared. So what is the square root of 2 plus 2, or the square root of 4, which is 2? And now our theta ends up being, how about tangent of theta is y over x. So square root of 2 over square root of 2 in quadrant 1, which gives me theta is kind of like what we did before. That would be our pi over 4. So this would be 2 cosine of pi over 4 plus I sine of pi over 4. So to multiply these two numbers, z1 times z2, once again, it's the product of the radii. So that would be 2 times 2, and then cosine of pi over 12 plus pi over 4 plus I sine of pi over 12 plus pi over 4. So pi over 12 plus pi over 4, that would be pi over 12 plus 3 pi over 12, or 4 pi over 12. So that'd be 4 cosine of 4 pi over 12, aka pi over 3, plus I sine of pi over 3. Maybe I'll show that. Pi over 12 plus 3 pi over 12 is 4 pi over 12, or pi over 3. Let's highlight it to kind of show some, distinguish why we have that there. Now, we'll ask ourselves, is that an angle that we know? Yes, the cosine of pi over 3 is going to be square root of 3 over 2. And then the sine, oh, bad Mr. Beck, that would be 1/2. And then I times the square root of 3 over 2. So that would be 2 plus 2i squared root of 3. So even though this turned out to look very nasty at the beginning, when we combine it with our radicals, it ends up being a very beautiful answer. Now, either one of these answers are okay. Like always, what do the directions ask? In this case, I said if we know what that angle is, let's go ahead and put it in rectangular form, just so that we can have something that we're familiar with. If we didn't know the angle, we would leave it in its polar form, which is right here. Both forms are completely valid. Now, just what is it we want? And let's work with it. Now, the last thing that we have to do today is let's take a look at what we knew about this problem. So with Z1, let's figure out what angle does it take to get to Z1. And that angle, again, I'm going to do this in degrees just because it makes working with the numbers a little bit clearer. So Z1 had 315 degrees. Z2, which Z2 is teal color. So Z2 is this 90 degrees. And then Z3, it's right here. Z3 ends up being 225 degrees. Now, if you notice, I have this lined up that now we are dividing rather than multiplying. So if we divide, we subtract our angles, and we're going to end up with the angle of the quotient. So kind of looking at these together, if we are multiplying, let me highlight this in that different color that I'm using. If we are multiplying, what that means is we're going to add our angles, where if we're dividing, we are going to subtract our angles. And then the other thing that I noticed was if I take the product of these two numbers, their radii get multiplied together to get my new radius. So I showed that right there. Well, something similar should happen, that our radii now, not that if we multiply them, but if we divide them, then the radii will end up being the radius of our new number. So let me show that. Change colors quickly. So if I take my Z1 has a radius, and I kind of teased you again, that radius ends up being 8. So if I take my radius of 8, and then the radius of Z2 is 2, and altogether, the radius of Z3 ends up being, we can see that as 4. So if we divide our radii, then we'll get the radius of the new answer, or we'll get the radius of our new complex number. So that would be this portion of it, that if I divide my two complex numbers, I will first divide my radii, and then I will subtract my angles, putting it into its complex form. Simple as that. So last thing that we get to do today would be, let's do this in that red color, that if I want to take Z1 divided by Z2, so that will be 14 divided by 2, because I'm dividing my radii, and then cosine of, now it's going to be subtracting, so 2 pi over 5 minus pi over 10 plus I sine 2 pi over 5 minus pi over 10. So 2 pi over 5 minus pi over 10, that would be 4 pi over 10 minus pi over 10, which is 3 pi over 10. So 7 cosine of 3 pi over 10 plus I sine 3 pi over 10. This is a perfect example of, do I really know that angle? Nope, so I'm going to leave this in its polar form. And then, very last problem. So sad that it's the last one, but Z1 divided by Z2. Once again, I'm going to divide my radii, so 2 divided by 2. Remember the radius of that one was 2. And then cosine of pi over 12 minus pi over 4 plus I sine pi over 12 minus pi over 4. Didn't leave myself enough room there. So 2 divided by 2 is 1. So 1 pi over 12 minus pi over 4. So that would be pi over 12 minus 3 pi over 12, which is negative 2 pi over 12, or negative pi over 6. So that would be cosine of negative pi over 6 plus I sine negative pi over 6. Cosine of negative pi over 6 is square root of 3 over 2. And then our sine of negative pi over 6 is negative 1/2. So square root of 3 over 2 minus 1/2 I. So multiplying and dividing our complex numbers. Last technical difficulties that I'm experiencing here. Has to do with, once again, if you're multiplying complex numbers in the polar form, multiply the radii, add the angles. If you're dividing the complex numbers in polar form, you divide the radii, subtract the angles. So hopefully you learned a lot, and all of this is kind of the setup for using de Moivre's theorem. And that's going to be what our day 2 exploration is going to be about. So hope you enjoyed this. Remember, I've got your back and you've got your back.